All right, welcome back. This is the part 2 video to finish up section 1.6 notes. We ended up on number 13. So if you remember, we were talking about using the end behavior rules for horizontal asymptotes to help you find the limits. But sometimes problems are a little bit tricky, so you got to be careful when you do that. Okay, so this page has a couple problems on it that just are limit problems that you just have to think about a little bit with the end behavior rules. All right, so look at number 13 and number 14 for that matter. We have one part of the fraction which is just a polynomial, but then the other part is a radical. Okay, so when we're thinking about finding the highest power of x in the denominator, I have to think about the fact that I'm taking a square root. Now I can't take the square root of this problem. Okay, I can't break it apart, but I can think about the fact that the square root of x squared would be x. Okay, so the highest power in the denominator, I can think of it two ways. I can think of it as 1 over the square root of x squared. I can also think of it as 1 over x, right? Those are the same thing. So when you have a problem like this, if it's a square root, then you're going to write it this way. If it's not a square root, then you'll write it this way. So when I multiply the numerator by the highest power in the denominator, I'm going to use that format. But when I multiply things in the denominator by the highest power in the denominator, I'm going to use this format because I have to multiply radicals by other radicals. Okay? So it's the same thing. It just looks a little different because of the radical. All right. So same process, we're going to do the limit as x goes to infinity. Multiply everything in the top by 1 over x. So 3x times 1 over x will give you 3. And then minus 10 times 1 over x is 10 over x. And then in the bottom, we still have the square root. Okay. So we're going to multiply 16x squared by 1 over the square root of x squared. So the x squares will cancel. And then 5 over the square root of x squared. Oh, just x squared. It's already under the radical. Okay. All right. So again, anything that's over x goes to 0. So now we are left with the limit as x approaches infinity of 3 over the square root of 16. So that gives you 3/4. Okay. All right, so same rule goes here. What is the highest power in the denominator? That would be x to the first. So I'm going to write it in the numerator in its radical form, which would be x squared. And then in the bottom, I would write it as that. Okay, so it's just got to keep with the same format of the problem or in that part of the fraction. All right, so the limit as x goes to negative infinity. So let's talk about that for a minute before we go any farther. So you have to be careful on problems that go to negative infinity. Positive infinity, all the numbers stay the same, whatever their signs are. When we go to negative infinity, they may or may not change, okay? So when I'm looking at this square root problem, I know that when I take the square root of this number, it's going to be a positive number, right? No matter what x is, what negative number x is, I don't care how big it is, when I square it, it's going to become positive. And even if I add its negative, this is going to be bigger. So the number in here is always positive, square roots are always positive, so this is going to be a positive number up here. But down here, as x gets bigger, or x gets smaller and smaller, as it starts going to negative infinity, think about it. You put negative 2 in here, negative 3 in here, negative 4, negative 5, negative 6, negative 1,000. This denominator will be negative, right? So I like to do this ahead of time because I know that my answer, whatever it is going to be negative now because I'm going to have a positive number divided by a negative number. Some instructors will teach you to use this symbol here. So we would multiply everything by 1 over negative x, and that'll change your sign as you go. And that's fine as well. We'll do that. okay? I just want you to see that if you don't do that and do the preliminary work, you're going to end up with the same answer, okay? Now, I'm not going to put it here because when I square the negative number, it's going to be positive anyway. So this up here is always positive. Here's my problem down here. All right, so let's go ahead and multiply the top by 1 over x squared. So it's a square root in the top, so we're going to leave it. So 9x squared divided by x squared is 9. X times 1 over x squared will give me 1 over x. And then 1 will give you 1 over x squared. All right, in the denominator, 2x divided by negative x gives you negative 2. And then 1 divided by negative x, negative 1 over x. So this goes to 0. All of those go to 0. So we are left with the limit as x goes to negative infinity of the square root of 9 over negative 2, which will give you that negative 3/2. Okay, so I knew that up here that it was going to be negative, but that's the way that you would do it. The only reason I show you that is because it's very easy to forget about this. So in my head, I just got to be real careful, and I know most problems go to infinity, I'm good to go. Soon as I see negative infinity, I need to do some thinking about what the sign of the answers are going to be. Okay, so just be very careful with that. All right. 15 is just a graphing problem, just to, again, trig. So we have the limit as x goes to pi over 2 from the left, and then 16 is the limit as x goes to pi over 2 from the right of the tangent of x. So we gave you the graph of the tangent of x. You should know what the tangent of x looks like. You should know where its asymptotes are, which are pi over 2 and 3 pi over 2. Okay, and there's more of those, but that's the first cycle of it. So if I'm looking at pi over 2 from the left, that means I'm coming from pi over 2 from this direction, which means that is heading towards positive infinity. And if I look at heading to pi over 2 from the right-hand side, that would be over here. That side heads to negative infinity. Okay, we didn't ask you the final question, which is what is the limit as x goes to pi over 2 of tangent of x? But if I asked you that now, hopefully you would tell me that this does not exist, right? Because the two sides are not going to the same thing. Okay, so just graphically looking at that, that is what we would get. All right, on number 17, this typo on the radical. So this is what it should look like. So they extended the radical a little bit too long. So the minus x should not be under the radical, okay? Should not be under the radical. That's what you should be working on. So either cross it out, rewrite it, okay? That's what you should have. So I'm going to rewrite this. All right. So that's what it should look like. Okay, so without a calculator, how do we solve this algebraically? So radicals are involved. One's a radical, one's not. So remember the little trick I told you earlier when you have a radical is you always want to use the conjugate. Well, if you're using a conjugate, that means you have to put the problem, write it as a fraction. So we would have to write it over 1. Okay, so the only way to do radicals is use the conjugate. All right, well, what is the conjugate? Conjugate would be the same problem, square root of x squared plus 7x plus 1. And instead of minus x, we would do plus x. And whatever you do to the top, we got to do to the bottom. Okay. All right, so remember what I told you. You don't have to do anything to the bottom. You're going to leave it alone, and then you're going to FOIL the top because when you FOIL conjugates, the outer and the inner will cancel out, right? So not a lot of work to do here. Trick is that you know to use the conjugate. Okay. All right, so if I multiply the square root of x squared plus 7x plus 1 times itself, the square roots undo each other, right? So we just end up with x squared plus 7x plus 1. The outer and the inner will be opposite, so they cancel. And then all we have to do is negative x times positive x, which is negative x squared. In the denominator, 1 times that, we're just going to leave it. We don't need to put the 1. So we just have x squared plus 7x plus 1 plus x in the bottom. All right, we can simplify the top a little bit. Get rid of those x squares. So we end up with 7x plus 1 in the top, right? Those cancel out. And then over our denominator. Okay, so now we're at the point where we're looking for what is the highest power of x in the denominator. All right, well, x is the highest power, and then remember, the square root of x squared is x. So we are looking at either 1 over x or 1 over the square root of x squared. That's what we're going to be multiplying by, depending on what our term is, okay? So we are going to have the limit as x goes to infinity. On the top, I'm going to multiply 7x plus 1 times 1 over x, that form. Now I'm going to break up the bottom. So on this part, the square root of x squared plus 7x plus 1, I'm going to use this form. So we're going to multiply that by 1 over the square root of x squared plus, and then for x, I'm going to multiply it by this form. Okay? So I've multiplied every term by 1 over x. I just used the correct form so that I could do the work. All right, so let's see what we end up with. So multiply 7x times 1 over x, that's 7. Multiply 1 times 1 over x, that's 1 over x. In the bottom, square root. X squared times 1 over x is 1. 7x times 1 over x squared would be 7 over x. And 1 times 1 over x squared would be 1 over x squared. And then lastly, x times 1 over x is 1. Okay. All right, things go to 0. Cross that out, cross that out, cross that out, right? All of those go to 0. Now be careful. Be careful with this 1 being out here. So now we're ending up with the limit as x goes to infinity, 7 in the top, square root of 1 plus 1. So we end up with 7 over 1 plus 1 is 2, so 3.5. Okay. All right. Now, that's a hard problem. Let's check to see if we're right. Okay. So I'm going to go to my calculator and I'm going to put in my problem, my original problem. Okay. Square root of x squared plus 7x plus 1 under the radical, and then make sure the minus x is not under the radical. That was the original problem. Okay, and let's go to the table. And now x is going to infinity, right? So let's do 100, 1,000, 10,000, 100,000. So you can see that the limit as we get to infinity is getting closer and closer to 3.5, right? Okay, so calculator way obviously much quicker than algebraically, but again, remember, this part of this class was meant for no calculator, so you guys got to work your brains a little bit starting off. Don't get lazy and just use your calculator, okay? Make sure you know how to do these. All right, I've added one more problem, okay? I didn't put it on Canvas, so I know that. So I'm going to put it up here. I like to do this with you now because, again, graphing, we don't give you guys enough practice on it. And so I kind of like to make sure that you can do this, okay? Disregard that page number. We're just adding this. So if you want to take a minute, we're going to sketch this graph based now on things that we've learned. So we have the limit as x goes to plus or minus infinity of f of x being 0, okay? We have the limit as x goes to 0 of f of x being negative infinity. We have a ordered pair, function value f of 2 is 0. The limit as x goes to 3 from the left of f of x is infinity, and the limit as x goes to 3 from the right is negative infinity. So if you want to pause this, write this down. We're going to graph this. So take a minute and write it down so that then we can kind of go through it. So pause if you want, or watch me and then pause it and go back and try it again. All right, but the first thing I want to look at is what does each of these pieces give me? Okay, so again, you have to understand what x is approaching. Is it an end behavior? Is it an asymptote? Is it just a function value? So that's what we're going to do right now. All right, so first and foremost, when x goes to infinity, okay, so x is going to positive infinity this way and negative infinity, that's an end behavior. Okay, so this right here is telling you what's happening at the end of the graph. That's an end behavior. Okay. All right. Check these out. The things that go to infinity, okay? Any number, it's not infinity. When x goes to infinity, that's what's happening at the ends of your graph, first and foremost. When you have x going to a numerical value that gives you a limit of infinity, those are vertical asymptotes. So this is a vertical asymptote, this is a vertical asymptote, and this is a vertical asymptote. So any value that goes to a number where its limit is infinity or negative infinity are vertical asymptotes. And this obviously is a function value. So I'm going to start there. That's easy. F of 2 is 0. Now, since I know these are vertical asymptotes, I'm going to put in dotted lines. So at 0, kind of hard to do. This is an asymptote right here at 0. Okay, make it a little bit thicker. And then this is both 3. So at 3, I have an asymptote. So asymptotes, usually represent them with a dotted line so that we know you can't cross those lines. Okay, you cannot cross a vertical asymptote on a graph. All right. Well, let's see what's happening at these vertical asymptotes. What's happening at 0? On both sides, because there's no plus or minus there. So on both sides of 0, from the left and the right, we're going to negative infinity. So on both sides of this asymptote, we're going to negative infinity. We're heading this way, we're heading this way, okay? All right, we gotta go through that point. And then what's happening at 3 on the left over here? Well, when I go to 3 from the left, I'm going to positive infinity. So that's up here, right? 3 from the left. So that means this graph has to do something like that. It has to go through that point. And it has to come this way, it has to go that way. I don't know exactly what it's doing, but something like that. All right. Now, let's look at the right side of 3. On the right side of 3, I'm going to negative infinity. So as I come this way to 3, I'm heading this way. So that would be down here. Okay, and lastly, I can do my end behaviors. Where am I heading on the end of the graph? I'm heading to 0. Okay, here's 0. So I'm heading to 0 this way, and I'm heading to 0 that way. So there's the sketch of that graph that has those limit values in the function value at 2, 0. Okay? So you need to be able to graph these to help you answer questions and, again, really understand a limit value. Okay? All right, so that does it for section 1.6. Work on your web work assignments. Get the notes check quiz done. Email me if you have any questions, okay? All right, take care.